So before we start, are there any questions regarding the previous material? So far we have covered the topic of formulations. We have gone over some dual and primal bounds. We also considered how we can code problems into computer and ask it to solve it. What we haven't done yet is knowing how to actually solve the problems, right? So we know how to bound the solutions, but we have no idea regarding how to theoretically construct an algorithm that would solve a problem for us. So before we actually begin talking about solutions to the problems, we need to concretely define what the problem is. So here I present you three definitions. The first definition is an instance of a problem, or in other words, you can think about it as a concrete problem from our lecture on GrobbyPy, or on on the computer implementations of GrobbyPy. You probably remember that when we actually substituted numbers into our code, we were defining a concrete problem, and this is basically an analog. So mathematically, I'm going to be referring to it as an instance of problem. If you're given a family of sets to which your parameters might belong to, you're defining a problem. In other words, it's like, for example, you can think of the general problem, the non-concrete problem with parameters instead of concrete numbers is the analog of a problem. So you can additionally, besides just introducing parameters, you can also bound the values of these parameters and say that the parameter sets belong to a particular subspace, and that would define your problem. A set of problems is called a class of problems. There are several classes of problems that you can think about, but the most important for us is going to be the set of the class of problems that are polynomial time solved. At least within this lecture, when we're going to be talking about easy problems, specifically those that have polynomial algorithm in terms of the size of the problem. The size, I mean the length of the description. So to summarize, you have an instance of a problem, which is the concrete problem given to you with the specific values, the specific numbers. A set of such instances is called a problem, and a set of these problems is called a class of problems. Obviously, both the problem and the class of problems needs to be defined, like specific class of problems needs to be defined. Any questions on this stage? Is it clear with the definitions? Cool. For those who are late, would you like me to repeat something?
I would appreciate it, but you don't have to.
Okay, so we defined three definitions. First is that an instance of a problem, which is defined with a particular set of numbers. Then a set of these instances forms a problem. A set meaning that you define where exactly your parameters belong to, which subspace, or what exactly is the ordering of the parameters. And then a set of such problems is called a class of problem, a class of problems. And we're going to be specifically interested in the class of polynomial time solvable problems, those that are for which there is an algorithm to solve a problem in polynomial time, in terms of the length of the description of the problem. Is that clear? Okay. Here I tried to summarize the main easy problems and what exactly makes them easy. So first of all, I would like to say that when we are talking about easy problems, we are talking about those for which we know there is an algorithm that leads to the exact solution. The set of hard problems, on the other hand, is a set of problems for which we don't know if there is one. So we haven't proved that there is none, but we haven't found one. So since the easy problems are a more constructive object, we can specifically define which algorithm solves them. Therefore, we can classify our entire space of easy mixed integer programming problems into classes according to which algorithm solves them efficiently. If we assume this approach, the most natural one would be to first classify the problems that can be solved by just trying to find a dual bound. So if we take a problem, we apply an algorithm that finds a dual bound for us, and it turns out that it actually finds us the dual bound and the primal bound at the same time. Therefore, it solves the problem. Similarly, we can define a class of problems that are solvable with an algorithm that provides with a primal bound. If we can just show that if we apply an algorithm that results in a primal bound to a problem, and in turn we will get both primal and dual bounds, then we can conclude that the algorithm that should be providing us actually a primal bound actually solves the problem completely. And then there is kind of a third kind of like space of or subclass of problems that are solvable with other methods, such as the dynamic programming method, which is not really neither neither the dual bound defining nor the primal bound defining algorithm. We will look into more details about the specific problems that are listed here. But right now, what you should probably realize out of this picture is that there are three main classes that we're going to be talking about. One is related to dual bounds and specifically the LP relaxation. The other is the one that's related to primal bounds and specifically the greedy heuristics. And the third is the one that can be solved with the dynamic programming approach. Any questions regarding? Yep. Right. That's a great question. So, if you are talking about a problem here, you need to define this family of sets to which X can belong to, right? So this set X should be encoded somehow into a machine. So each set X would have a length, which is let's say n, and then a problem would consist of like a problem would correspond to a set of such x's, right? This set paragraphic x is the set of such x's, and for each x there is a unique n, or like, okay, it's not really unique, but it's defined up to constant. So it's there's a correspondence between x and n, and we should like, if we are given an algorithm that solves a problem, that means that there's an algorithm A that gets an input x and outputs a solution x, which is the correct one for the simulation problem. We should expect this algorithm A to be running some amount of time, which is dependent on the size of this x. And when we are talking about polynomial time solvable, we are saying that this time of a defined like when it's being run on an input of size n is polynomial solvable. Right. And I mean, we actually also here we imply that the amount of resources that A uses also scales with n. That's a great question. Any other questions? It's good. Okay. So I just have to say here that normally we would know that the MIP, the mixed linear programming problems, could not be solved. We do not know how to solve them. Most probably they cannot be solved in polynomial time. But here we are looking at specifically MIPs that are solvable in polynomial time, and we call them easy MIPs. That's it. Okay. And when I say solvable, I mean that it's solvable in polynomial time with a statistic. So let's start by taking a look at the problems that are solvable with LP relaxations. So just to remind you what LP relaxation is, having a problem of this form when you minimize a linear function subject to x belonging to some set x, and this x having a description p, which is a polytope, just to remind you. We are saying that an LP relaxation of this problem of minimization is a minimization problem that consists of minimizing the same objective function over the formulation with which x is given, right? So what does it mean? So we know that LP relaxation would give us a dual bound, right? So in this particular case, if we are solving minimization, we're kind of expanding our set. Therefore, we should fall lower than we normally would if we were to just solve the IP. Therefore, it will be a lower bound on the optimal solution. And what we expect if we say that we have solved the problem is we would expect that we have found the solution to the LP relaxation is in fact an integral solution, or in other words, it does belong to x. Together with, like, we know for a fact that it is going to belong to p, but we also expect that it is going to belong to x. Therefore, it's going to be integral. That's what we would expect if we are saying that LP relaxation solves the problem completely. From the linear programming theory, so now we know that we need to look for cases when the optimal solution to our LP relaxation is integral, right? Is this clear? Any questions here? Okay. From linear programming theory, we know that the solution to the LP, any LP problem, can be decomposed into two parts. One is called the basic variables, and the other part called non-basic variables. The non-basic variables consist of a vector of all zeros, and the vector of basic variables is can be rewritten in this form. The inverse of b times the vector, the inverse of capital B times the vector b, the right-hand side, where this matrix B is a particular submatrix of matrix A that participated in the formulation. So to show you an example, if we have matrix A, and then we multiply it by X, we get vector B. And what we are saying here is that there is a submatrix B and a subvector XB, such that okay, I need to. So this submatrix is actually like this, and it's square. It's a square submatrix, and our XB is going to be the inverse of this matrix B times the right hand side. That's like the specific components of the right hand side. We know that the right hand side, we can assume, like we can normally assume that let us assume that the right hand side B is integral. So all of the entries of the vector B are integral. In this case, we only, like, in order to guarantee that the vector X star is integral itself, we only need to take care for this inverse of B to be integral as well. And if the inverse of B is integral and this vector is integral, then by multiplying the integral matrix by an integral vector, you would get an integral vector. Therefore, our solution X star that we get out of the LP rotation is going to be integral. Is this a complete line of thought? Any questions here? Would there be any question? No? Okay. So again, what we need to show is that the inverse of B is integral. But by the primary rule, we know that the inverse of B can be written as the adjugate matrix of B divided by the determinant. So it is like a matrix. It is like the inverse is some matrix divided by the determinant. If we want, if we would like the result of this to be integral, then we should expect this this matrix to be integral and this determinant to be +1 or -1, because otherwise we would never be able to follow which exactly integral numbers here get divided evenly by this determinant. So we would like to assume that this determinant is B. So I will come back to this matrix a bit later. What if you don't remember it? So right now we are at the stage that we would like to demand this matrix to be integral and this determinant to be +1 or -1. And in fact, it turns out that it is a sufficient condition that if we demand that all if we demand that the determinant of B is +1 or -1, and A is an integral matrix, then XB is going to be an integral matrix. How to show this is basically by taking a look at what adjugate of a matrix actually is. So an adjugate of a matrix is a matrix of the cofactor matrix transposed. A cofactor matrix is a matrix of of cofactors. So let me write this down. So if we have a matrix A, we have an index I and an index J, an intersection. We can define a submatrix, an IJ submatrix. Let's call it Dij. It is a matrix that is formed from A after we have crossed out the Jth row and the ith column. So the matrix formed by these entries is called Dij. And then we form Cij, which is the determinant of Dij. And then we essentially what we are doing is okay. So and it must be multiplied by -1 to some power I plus j. We know that there is a very important property of a cofactor is that the determinant of any matrix can be decomposed into sum by one of the rows or one of the columns. So if we have a matrix A and we have a row, we can say that the determinant of A is the summation of over I, where I goes through each of the elements in the row. Aij, which is the jth row, Aij times Cij, where Cij is this determinant right here. It is a very important property that we'll reuse later. But right now, I just wanted to stress your attention on the fact that this cofactor matrix is a matrix that that is a transpose of this matrix C. And since we know that if we assume for a moment that all of the subdeterminants of matrix A, if matrix A is such that all of the subdeterminants, meaning that whatever submatrix you get, you are picking from your matrix A, its determinant is going to be -1, -1, 0, or +1. If this property holds, then the cofactor matrix is in fact integral itself. So it is kind of a very nice property. It is in fact a very nice property to have. Okay, so I will not stop in details on what determinant of a matrix is, because I believe everyone knows what it is. Okay.
If that Cij is a submatrix there, then according to your definition, shouldn't Cij be a number?
You are right. So it is. So I should have put Cij over here. Let me correct it here so that I don't forget. The Cij really belongs to here. Yeah, it is a determinant. It is in fact a number.
So it's not the determinant. Cij is the number and the submatrix is Cij.
Yeah. Right. Yeah. Okay. Cool. So now that we know that it is a cool property to have, that all of the subdeterminants are equal to -0 plus -1 plus 1 or 0, we can define a totally unimodular matrix, which says exactly that. It says exactly that it is a matrix for which every subdeterminant or the determinant of any squared submatrix is -1, +1, or 0. Then we have that the propositions that a matrix A is totally unimodular if and only if its transpose is totally unimodular. And the second property is that if we have attached an identity matrix to matrix A, it still must be a totally unimodular matrix. It's quite straightforward to show these properties just by looking at the properties of the determinant. So from these two properties, we can get the proposition 3.1. I won't stop on that in details. The proposition 3.2 is more interesting. It's saying that a matrix is totally unimodular. It gives us a sufficient condition for matrix to be a totally unimodular matrix. So we say that a matrix is totally unimodular if all of the following conditions are satisfied. And then we are given three conditions, which are remarkably easy to verify. Even though it is quite hard to check all of the subdeterminants, like it's tedious work, we are presented with a relatively easy sufficient condition. So let us take a look at this sufficient conditions. Are there any questions before we? So the first condition is quite simple. It just demands us all of our entries of the matrix to be -1, 0, or +1. It is in fact a necessary condition too, because if it's not the case, then a very simple submatrix that consists of a single number will not satisfy the definition of total unimodularity. Therefore, it is a necessary condition. Then the second condition is telling us that each column contains at most two non-zero coefficients. So whatever column would be, since we know that our coefficients are -0, -1, +1, and 0, we know that all of the entries in this column must be equal to 0, except for two of them, which are either plus or minus. It is from the proposition 3.1, we can also assume, like, come to the conclusion that if this property is satisfied for the rows instead of the columns, then like it still holds. Like we can just show that a matrix, a transpose matrix is totally unimodular, and then transpose it, and it's still totally unimodular. So we're good. But here we're going to be talking about columns specifically because we're going to be using this property for columns in the end. The third condition is more kind of interesting. It says that there's a partition of the set of rows. So the set of rows can partition into two parts. First part is called M1. The second part is called M2. Such that for each column that we are considering on J, the summation of aij's that belong to M1 minus the summation of mij's that belong to M2 is going to be equal to 0, which basically says that well, if we have our like +1s we have all over here, and then +1s we have all over here, then we can like make this division into two parts and some plus ones will be included here on the left hand side, and other plus ones will be on the right hand side, and they will cancel each other. It is a kind of a nice property. Sometimes it's simplified by just saying that well, each column that contains each column that contains two non-zero coefficients has to have plus one or minus one, but that's an oversimplified condition. We don't need that at this stage. So, are there any questions regarding the conditions, their structure, before we get to example and then to proof? Yep.
Does M1 have to be above M2?
No, it can be any subset. And M1 can be this subset, and M2 can be this one. Yeah.
So both M1 or can M1 or M2 be the empty set?
Yeah. Yeah, we will actually see an example when it is. Very good question. So let's take a look at this example here. First of all, we can verify that the first condition holds, because those are only very simple numbers here. The second condition can also be verified, just like if you look at each column. And the third condition does hold as well. And to see that, you can just take M, the beta being equal to all of the columns, 0, 1, sorry, all of the rows, 0, 1, 2, and 3, and M1 being equal to M, and M2 being equal to M, just like you just now. And therefore, this matrix is totally unipolar. Every squared submatrix has a determinant of +1, -1, or 0. Is it clear how I applied this? Cool. So now let us turn to actually proving this nice condition. Proposition 3.2. Okay, so our condition is sufficient. Therefore, to prove that it holds, it is enough for us just to think from contradiction. So we have, let's say that we have a matrix that satisfies all of these conditions. It's called A, matrix A, and let us assume that it is not a totally unimodular matrix for a moment. Let B be the smallest square submatrix for which the determinant is not plus, minus 1, or 0. It must exist because it is not a totally unimodular matrix. Once again, this is the smallest. So B cannot contain a column with a single non-zero entry, otherwise B would not be minimal. How to see this is by utilizing that property that I mentioned regarding the decomposition of the determinant. Let me remind you quickly. What was the property? This one. The determinant of any matrix can be decomposed by its row or its column. So B is our minimal matrix. Minimum in terms of the number of rows, or it's just minimal, whatever. The determinant of D. Okay, so let us see. So we are saying that B cannot contain a column with a single non-zero entry. Let us assume that it actually does contain a column with a single non-zero entry. I'm right here. Let's denote this entry as +1, -1, and all of the other entries are equal to 0. Then our determinant, if we decompose our determinant by this column, we'll get the following. It's going to be a summation for I from 1 to n, a I j times c I j, where c I j is that cofactor thing that we introduced before, And this aij's would go over this entire column. Therefore, it will be just plus minus 1 times Cij. This entire sum is being reduced because all of the a's are actually 0. It's going to reduce to plus minus 1 Cij, where ij is the index of this plus minus 1. Therefore, there is in fact a smaller submatrix of this form, and we know that this determinant is not equal to does not belong to 0 plus minus 1. Therefore, this thing right here, Cij, also does not belong to the set 0 plus minus 1. And this Cij is a determinant of a submatrix of this form. So we just join this part, and this part. This is Dij. And Dij is in fact one element smaller than our original matrix B, right? Therefore, it turns out that there is a contradiction to our smallest assumption. Therefore, we are saying that there cannot be a column with a single non-zero entry. Any questions regarding this line of thought? No questions right now? Okay. Okay, so therefore we conclude that B can only contain 2 non-zero entries in each column. Now, by condition 3, adding rows in M1 and subtracting the rows in M2 gives the 0 vector, and therefore the determinant of B is equal to 0, and we have a contradiction. So what is done here is that we just take we take this matrix B, we take its rows, we add them with some coefficients, and we get 0. We get a 0 vector, right? That doesn't sound right, because that implies that all of these rows are in fact linearly dependent, and therefore the determinant of B must be equal to 0, even though we have assumed that it cannot be, it's not 0 and not plus minus 1. Do you agree with me? And therefore, we conclude that in fact B cannot exist. Such smallest square submatrix just doesn't exist, and therefore A is in fact totally unimodular. Is that clear? Cool. So now that we have understood what total unimodularity is, we haven't understood how to like quickly show for a good matrix that it's a totally unimodular matrix. We can say why it is important, actually, even though we have kind of seen this already. So the problem of the form specified above. The maximization, the IP problem. By the way, I'm talking here about IPs mainly, but it is obvious that there's an extension to mixed integer programming problems without any like change in any definition or anything. The problem of the form of an IP, where we specify to which subspace X, to which subset calligraphic X our X belongs to. This problem is solvable with the linear programming relaxation, where let me put this way actually. So our problem, this is where the definition of problem actually goes wrong. we're going to be only considering a set of instances of the mixed integer programming problems for which A is a totally unimodular matrix. Only this kind of problems. And B belonging to integral vectors. And we are saying that this problem is polynomial time solvable. And moreover, we can just demonstrate an algorithm with which it's solvable, and this is the linear programming relaxation, based on linear programming relaxation. It is also important that the statement about this problem does not really put any restrictions on the vector B. So B can be in any kind of direction, it can be any vector, and it's still gonna be it's still gonna be solvable with linear programming relaxation. However, the restrictions on A are quite significant. They are quite tight. It's not very common to come by a totally unimodular matrix if you just sample them from some random distribution. Therefore, it could be this kind of statement could be enhanced in a way by relaxing the condition on the matrix A and restricting the condition on B. And this result is called the condition of total dual integrality. You can read about this in that textbook, and I don't stop on that in details. But generally speaking, it's about relaxing conditions on A and restricting conditions on B. At the same time, we're saying that if we do not restrict conditions on B, then the requirement of totally unimodularity is necessary. Meaning that if A is not totally unimodular, you can always, for any A that is not totally unimodular, you can always come up with the vector B and vector C, for which the solution of the IP is not equal to the solution of the LP. So the linear programming relaxation won't solve the problem for the specific vectors B and C. Any questions here? No questions? Cool. Let us take a look at the examples of problems with totally unimodular matrices and submatrices. So let me come back to this picture here. So we had a whole class. The bigger class is the totally dual integral class, which is, as I said, allows you to relax some conditions on A, so it's bigger. Then there is a class of totally unimodular matrices, and then there are examples of totally unimodular matrices where exactly you can find them. And most of them are in fact in the realm of network flow problems, such as the shortest path, the transportation problem, and the maximum flow. Let's take a look at them. So the example of the minimum cost network flow is the following. So it is quite a general problem. You have a directed graph. There are some directions here, and you have a directed graph D. You have arc capacities HAJ for each arc. You have arc unit flow costs CIJ. So for each arc, you assign at least 2 numbers, and then there are demands BI for each node in the graph. So the demands are normally noted with arrows kind of coming from outside, because it's like the demand doesn't appear anywhere in the network. It comes from outside of the network, and the demands are going to be BI. I'm not sure. It should be DI anyway. Okay. So once again, a minimum cost network flow normally consists of a graph and a couple of numbers for each edge, and possibly a number per each node. The problem that we are trying to solve, the problem of minimum cost network flow, is to satisfy the demands on the nodes subject to satisfy the demands on the nodes while minimizing the flow of the cost of the flow through the edges. So through, let's say that there is a flow, like a demand of -1 at this node, and a demand of +1 at this node. Then a flow floating from this node to this node would be a flow like of unit 1. If Hij allows it, Hij is something that can limit our flow from above, and Cij, and the cost of such flow would be Cij, because it's a unit of flow of cost of Cij. If we write down this problem formulation, we will arrive at the following write up. Let's say that V plus of I is the set of outbound nodes. V plus of I is the set of edges, actually arcs, that are coming outside of the node. So if this is the node I, then this edge is outbound and this edge is outbound. Vi minus is the set of inbound nodes. For example, for this, it's this edge right here. So we are trying to minimize the total cost over. So our Xij is the amount of flow through an arc Ij. We are trying to minimize the sum over all of the arcs of Cij Xij, meaning the amount of flow through the arc times the cost of the flow through the arc over unit of flow through the arc. Now we need to formalize. So first of all, we need to formalize the constraint on the capacity constraint on each arc, which is this one. Xij cannot be negative, and it cannot exceed some fixed number Hij. There's also kind of an equivalent reformulation or equivalent restatement of this, where we actually have both upper and lower bound on the flow. But it isn't an equivalent restatement just because we can always just push our bounds so that the minimal bound is zero. Now we need to formulate the continuity of flow, the fact that our flow doesn't come from nowhere. It only comes from a negative demand, or the other way around. It comes from it comes from a negative demand, and it sinks into a positive demand. Also it doesn't get lost anywhere. So the amount of flow that gets into a node minus the amount of flow that gets out of a node must be equal to Bi, which is the demand at a node, which is the main continuity of flow constraint. Therefore, we have like two main constraints and a linear objective function. It's easy to see that all the constraints are linear. Therefore, we have formulated an integer programming problem of this minimum cost network flow. Right?
Would another formulation of the graph be acceptable to like vertices and non-vertices and outbound vertices? Like split like the vertex 1 with all the edges coming into vertex 1, and then having like a uncapacitated domesticated edge.
Sure.
To
Yeah, you mean having something like instead of this node, we replace it with a couple of nodes.
Yeah.
One of them having an outbound node, another one having an inbound node, and then there is a node between them, something like that. Yeah, but like the thing is that like even from this node there's an outbound. There's an outbound arc, right? It has to have at least one. But it is kind of possible to reformulate it this way. Why do you want it to be reformulated this way?
just in terms of like visualization.
Right? Yeah, it's a decent way to visualize it. I would say that yeah, this concept of having like of inbound and outbound nodes. Wait, am I missing minus there? Oh, okay, it's I instead of, so this is minus right here. It's not I. I hope this is obvious. Okay, I'll fix it. But yeah, this concept of inbound and outbound nodes is a very important one in graph theory. So yeah, if that helps, for sure, do use it, but be aware that it's quite common. Yep.
I think your in this formation example, x belongs to like z and like a plus. Does that allow it to be 0?
Yep.
Okay.
Yeah, and normal notation is z for just integer numbers, z plus for non-negative integer numbers, and z plus plus for something that is like strictly greater than 0.
Right.
So if you have just one plus, it's normally greater than or equal to 2 plus. But it really depends. But it's the most common notation I've ever noticed. Okay. Any other questions here? No. So let's take a look at the example of this minimum cost network flow. So our additional constraints here are in fact just consisting of a unit matrix. Like this constraints 0 less or equal than xij can be written as the identity matrix times x is less than or equal than something, and then the identity matrix times x is greater than or equal than 0. So this is just this just stacks together two identity matrices. If we are to not, so like we would like to represent our problem in the form that we are minimizing c times x subject to a x less than or equal than b. And what I'm trying to argue for is that okay, so after we have formulated it in this form, we would like to take a look at this matrix A and show that it is totally unimodular. So I'm trying to set up this matrix A so that it has a simple form. And I'm saying that our inequalities here are having the form of some balance equations. This let's say b x equal to some vector b. Yeah, okay, that'll be b. And ix less or equal than h and ix greater than or equal than 0. We can unite this all matrices into one. And what I'm saying is that if so, this entire matrix, or even we would need to do some manipulations in order to obtain this form, but these manipulations wouldn't change much the form of this matrices. So it's still going to be like something like an identity or like sum of two identities. Our identities wouldn't change the fact that our entire matrix is totally unimodular, as long as B is totally unimodular. Therefore, the main thing that we need to show in order to show that the entire matrix A is totally unimodular, we need to show that this matrix B is totally unimodular. For that, we can write down the matrix B. It's written right here. And now we can just take a look at it and tell me, according to the previous properties that we have noticed, we have witnessed. What can you say about this matrix? Is this a totally unimodular matrix? By any chance? You think so? Yeah. So all of the rows, sorry, all of the columns consist of exactly 2 plus minus 1, and they come in pairs. Therefore, we can take the M1 to be all of the rows and M2 to be.
Because every inbound has an outbound via.
Precisely. Yeah. Yeah. So this is where we're coming at. So you can see that at this specific example, this matrix B is totally unimodular, and in fact, in general, if B comes from the flow constraints, then our matrix, our entire matrix, is going to be totally a totally unimodular matrix. Therefore, all of the problems that are having this structure, all of the minimum cost network flow problems, are easy to solve with the linear programmable relaxation. Just because of this property that each edge, each arc has two ends, and since our columns here correspond to arcs, each one is going to correspond to the spot to which so each column corresponds to an arc, and each row corresponds to a node, a vertex. And each plus one is going to correspond here to an outbound kind of side of an edge, and minus one is going to be corresponding to an inbound side of an edge, and therefore they will always come in pairs. And therefore, it doesn't matter which graph you're working on. In fact, for any graph, corresponding matrix B is going to be totally unimodular, and when you join them, this matrix B with the identity matrices, it's still going to be totally unimodular, and therefore the entire matrix of constraints is totally unimodular, and therefore our minimum cost network flow problem is an easy one and can be solved with linear programming relaxation. Okay, so this is the proposition 3.4. Any questions here? No questions for now? Okay. Let's take a look at an example of minimum cost network flow. You know what? I think I'll leave it probably for later. We can come back. We can come back to it. Right now, I'll probably. Okay, let's try to go over this. So the minimum cost network flow example. A company that is manufacturing chairs that has 4 plants located around the country. The cost of manufacturing, executing, excluding raw materials per chair, and the minimum and maximum monthly production for each plant is shown in the following table right here. So we have 4 plants. We have a cost per chair for every plant. We have the maximum and the minimum total amount of chairs produced per period. 20 pounds of wood is required to make each chair. The company obtains the wood from 2 sources. The sources can supply any amount of the to the company, but contracts specify that the company must buy at least 8 tons of wood from each supplier. The cost of obtaining the wood at the source is for source 1 it's 10 cents, and for source 2 it's 10.5 cents per pound. And then we have shipping cost per pound of wood between a source and plant, which is shown right here. Okay. Then we have a distribution system that says that we are distributing to different cities from our plants, our chairs, and each kind of delivery costs us a certain amount of money. Also, we have some demand and some prices depending on which city the chair is being sold in. Okay, so we have price for it and minimum and maximum demand that we need to satisfy. The minimum cost network flow problem model for this example can be formulated with the following graph. So here it is more. It is in a way more natural to have 3 numbers per edge, addressing both upper and lower bound on each edge. Just because we have sometimes our production is limited from below, therefore we would need a lower bound too. But generally speaking, it is always like for each edge we need to specify cost, a lower bound on the edge, and an upper bound on the edge. Here you can see that we need to okay. So first of all, we need to understand what exactly is our flow, because at some point we are kind of converging. On one side, it is wood that's being passed through network. On the other side is chairs. So like having like coming to the common denominator is quite easy here. We can just talk about money on both sides of the network. So the problem of acquiring wood from a source, wood is modeled with this part, where we have some like general nature node 1 that distributes wood to the sources 2 and 3. Then we have a redistribution of wood into the factories. So from the 2 sources of wood, we have distribution of wood into four different factories. Correspondingly, each unit of flow through an edge of this form would correspond to a unit of wood that is being sent from one source to a factory. Then the process of manufacturing, to model the process of manufacturing, we're actually splitting every single factory into 2 nodes with an edge between them, which models the process of manufacturing a chair. And then we have the distribution from 4 factories into 4 different cities, which is also captured through part of network, like this set of edges. And in the very end, we have the consumption of chairs that is being gathered into the node 16. To omit actually defining the demands on all of the nodes, even though we only have demands in the nodes 1 and 16 because chairs do not appear anywhere else in the network. We just decide to close loop the system. So each unit of flow, it will have to circulate in this network. This circulation arc does not have any capacity, so it's because the capacity is infinity. It doesn't have any cost. It just needs to. It's just needed for the purpose of kind of making sure that our flow here is coherent with the continuity constraints that we have set for our minimum cost network flow. Is this model clear? Okay, so it's very important to know how to formulate minimum, like it is very important to recognize and formulate minimum cost flow models, because first of all, they're extremely common in practice, and second of all, they're very easy to solve. So if you have seen like an integer programming problem and you were able to reformulate it in this form, then you have won a lot of computation.
How do we, so is there a place where you can see how this is put in like program formulation, like actually like constraints?
Yeah, so I don't think I put this down, but what you would need here is you would need to put down. So first of all, so everything that is being defined here is in fact like also, so all of the demands B that were defined here, the right hand side B, are equal to 0, right? Because we added the circulation flow arc that avoids all of the demands altogether. Then we know that these two numbers are going to be like non-zero for many of the arcs. So we like instead of 0, we will have some lower bound L, and instead of H, we will have some upper bound U. And therefore, our only non-trivial part in the formulation is going to be the one that is set by the graph. I don't have it anywhere on the slides, but it's pretty straightforward. So when you have an arc, you add a variable to the problem, and you into the for each. So you have to, in order to construct the matrix B from a graph, you would need to pick an arc. You say that my arc is say 1, 3, 1, 3, or x 1, 3. You pick node 1 and node 3, and for one you assign +1, for other you assign -1, and all of the other you fill up with zeros. And this will give you the matrix B if you have a network. And the other matrices are I's, and the right hand side are going to be U and the vectors. Sounds good? Yeah. And the cost is just the third number on times the xij. Okay. Any other questions here? No questions? Good. The other, so one of the important special cases of minimum cost network flow. Wait, I'm not actually covering it here. Okay, so let's take a look at another example of using total unimodularity for showing for showing things and for solving things. Here we are considering also a flow problem, but it is not. It's kind of a special case of a flow problem, because it's called the max flow problem. Before we were considering min cost network flow that was aimed at minimization of C times xij, Cij xij, and then we had like constraints on continuity of the flow and also capacity constraints. In the max flow problem, we set all of theCij's to be equal to 0, and we only set CTS to be equal to -1. Therefore, we can, instead of minimization, we have maximization, and we are maximizing the flow from an arc T to an arc S. So this is the exact case when we have a sync node S. We have also sorry, probably it should be start and terminal, and the entire network is located between the start and the terminal points, the start and the terminal nodes, and then we have a circulation arc that goes from T to S, and we would like to maximize the amount of flow that is passed through this arc. It is obvious that the amount of flow that is passed through this arc is going to be the amount of flow that is being passed through this entire network, because all of the flow that is passed through this entire network is going to be returned through the circulation node. Therefore, this problem is called, it's a special case of the min cost network flow, and it's called max flow problem, because we are trying to understand what's the maximum flow that we can possibly put through the network. One way to kind of like one obvious utilization of this formulation is with the logistical network. When you need to ship as many vaccines as possible from a manufacturing plant to a particular city, and you have just so many roads, and you just pack them with your trucks and see how many vaccines you can possibly ship within one day if you have this many roads. Okay. We also have another problem here. Another problem is called the min cut problem. Min cut is kind of from a different world. If you kind of see it from this perspective. Min cut aims to find a set X that contains the start node, and it does not contain the terminal node, set S. Sorry, set X. A set of nodes such that the size, the capacities of the edges that kind of go through this set X, that goes from set X to nodes that do not belong to the set X, or in other words, it's the cut that we are talking about. So the cut of the cut between the set X and the complement of the set X is minimal. So we are minimizing over all of the set X. The value of the cut, which is the summation over all edges or all arcs, such that the start point of an arc does belong to X and the end point of an arc does not belong to X, of the capacity of an arc. And we also have the constraint that the start node must belong to X. This problem, the problem of finding such a subset of nodes is called the minimal cut problem. So we are considering two problems: the max flow problem and the min cut problem. Any questions regarding the formulations? Okay. Do you agree with me that they don't appear similar at all? Like, the first one is kind of integer programming problem. The second one is combinatorial problem. It's not quite clear. It turns out that max flow min cut is a strong dual pair. So one is in fact a strong dual of the other. And we would like to try to prove it. And to prove it, we will use extensively the fact that minimal cost network flow is based on a total universal matrix. Let's try to do it. So first of all, we need to write down the dual of the max flow LP relaxation. So first of all, the LP relaxation of max flow is just max flow with the real numbers, the set of real numbers here. The dual of that problem would consist, first of all, the variables would correspond to the two constraints that that appear in the primal. So the first set of constraints corresponds to u, the vector u right here, and the second set of constraints is going to correspond to the dual variable w. Yeah, w. The objective function is the right hand side times the vector of variables, which in this case, since our right hand sides that corresponds to that correspond to the vector u are all equal to 0, it's just the summation over all arcs of hij times wij. Then the corresponding constraints on u and w can be written as follows. It's the difference between ui and uj plus wuij is greater than or equal than 0, and special constraints for all arcs except for an arc that is the circulation arc. For the circulation arc, we have that ut minus us is greater than or equal than 1, just because we had 1 over here in the objective function. Okay, any questions regarding construction of the dual? Okay. Without loss of generality, we can assume that us for the optimal solution, the value of us is equal to 0. Just because if it's not equal to 0, let us reassign all of the values to the value plus alpha. This will not change the value of w. This will not change the value of the objective function because u's do not participate in the objective function. Therefore, it will still be an optimal solution. Therefore, u's only defined up to a particular scalar. So we can safely assume without loss of generality that us is equal to 0. Since our problem is totally unimodular, our optimal solution u star w star, which is the optimal solution of the LP relaxation, aka the optimal solution of the dual of the LP relaxation, must be an integral vector pair. So both u star and w star, which solve this this problem, it must be must be integral vectors. This solely comes from the total unimodularity of minimal cost network flow. Then is everything clear up to this point? Have I lost someone? Not yet. Let us define a vector, a set X, a set of nodes. It's the set of nodes for which uj star is less than or equal than 0. So it's a negative number or 0, non-positive number. Then the complement of the set X is going to be the set of nodes for which uj is greater than or equal than 1. Why it's 1? Why not 0? Yeah, but so it's uj less than or equal than 0 here. It could be greater than 0 here, greater than or equal than 0 here. It's an integer, right? So it's not greater than or equal than 0 just because uj is an integral number, and using the fact that so therefore we can construct the following series of inequalities. Where the first inequality comes from the fact that UH is greater than or equal than 0 and U star is greater than or equal than 0. So if we just throw out some entries in like from the sum if we throw out some summons, we will end up with the number that is less than or equal than the previous number. And the second inequality comes from the fact that uij star is greater than or equal than uj star minus ui star, which is the corollary of this inequality, and then it's greater than or equal than 1 just by definition of x and the complement of x. Therefore, we have the second constraint as well. Therefore, we have shown that the optimal value of the linear programming relaxation is in fact greater than or equal than the objective value of the minimal cut problem if we substitute x defined this way, for like at x defined this way. Therefore, we can okay. So therefore, we have obtained an upper bound. So the solution of the relaxation, aka the solution of the max flow problem, upper bounds the solution of the minimal cut problem. Now we need to show that it also lower bounds. We can show this by defining so taking the optimal x for the minimal cut problem and assigning the following values to the nodes and to the arcs in the dual of LP in the following way. So we say that uj is equal to 0 if j is an x, uj is equal to 1 for j not an x, and then we say that wij is equal to 1 if ij belongs to a cut between x and the complement of x, and wij is equal to 0 otherwise. Then this would lead us to a feasible solution to our dual of linear programming relaxation, which implies that it is first of all, there is an optimal binary solution to this problem, to the dual of max flow LP, and S in fact does belong to the set capital X defined this way, and T does not belong to the X defined from the solution of the minimal cut problem, and therefore wij and also wij is equal to being equal to 1 marks the cut, and the objective value is the value of the cut. Therefore, we have obtained a lower bound on the solution of the min cut problem from a solution of max cut problem. Therefore, since they kind of upper bound and lower bound each other, we can conclude that their solutions exactly equal, which implies that they form a strong primal dual pair. Okay, any questions at this point? Sorry, are you talking about this point? So you're talking about this inequality here?
No.
This one?
Yeah. What is this from? Is this from?
So we define X this way.
Okay.
So we are given only the solution to the dual of max flow LP, we are given u and w that solve this problem, and we define x such that x is a set of nodes such that uj star is less than or equal than 0. We always can do that, right? Because our set our vector uj like first of all it assigns a value for each node, and also it is we have that ut minus us is greater than or equal than 1, and like we can essentially assume that our us is equal to 0. Therefore, our s is gonna be an x, and there will be possibly some other nodes in x, but they don't have to. So our set x is a feasible set, meaning that it's a set of nodes that is not empty, and s does belong to x. Does this make sense? So we have defined x this way, and after that we have shown that we have defined this x this way. We have shown that it is a feasible x, and then we have shown that the objective value of this specific x is less than or equal than the optimal objective value of the original problem of the dual OP. Okay. So the next kind of a big part of our course is going to be devoted to problems. So with the max flow mean cut, we conclude with the problems that are solvable with relaxations, in particular the dual bounds, the algorithm that provide dual bounds, and we are going to be switching to problems that are solvable with a dynamic programming approach. So the first, like probably the simplest problem connected with the dynamic programming principle is the shortest path problem. It's a good thing to start with shortest path because it's also a network flow problem. In this problem, we are given with like a graph, and our demands b are equal to 0 everywhere, but at 2 nodes. The node S and node T, the start and the terminal nodes. To each edge, we can assume that the capacity of an edge is infinite, and there's a single cost value that is assigned to each one in the graph. We need to find the shortest path from S, from the start node to the end node. And for that, we will be formulating an integer programming problem with variables xij, like corresponding to arc, and the value of this variable is going to be equal to 1 if in the solution we have like this as a specific arc does belong to a path, to the path that we have designed, and it will be equal to 0 if it does not. So, for example, here we have in this graph we have a path of this form, and xij for this edge here, for this arc here, will be equal to 1, and xij for this arc here will be equal to 0. Okay, so let's take a look at what exactly is the formulation. So here I just wrote down. So you can easily see that first of all, we can assume that our capacity of an arc is 1, just because we don't want to send more than 1 unit of flow, just because we have 1 and -1 as our demands. We also have continuity of flow constraints that I have written out as 3 constraints. They were written down as 1 constraint before. It doesn't really matter. I just substituted the particular numbers instead of BIs. But overall, it's important to note that it is, in fact, itself an example of mean cost network flow as well. So the past two, this problem and the mean cut max flow problem, all of this are problems that are special cases of mean cost network flow that we have introduced before. So it's indeed a very rich class of problems. Okay, so let me come back. Okay, so we have this continuity of flow constraints written down as 3 separate constraints. And we can write down the dual of the LP relaxation of the shortest path problem. So this set of integer numbers can be replaced with a set of real numbers, and then we can dualize the corresponding LP problem in order to obtain the problem in this form. Here, this D is in fact a vector. It's written down as it's a function, but in fact it's a vector with the same amount of with the same number of components as the number of nodes. We just represent the components as like in the parentheses. We are maximizing the D of T minus D of S subject to dj of minus di less or equal than Cij for all arcs. So this is the formulation of the dual, and here di minus dt can be interpreted as the length of the shortest path from T to I for any I. So here you can see that we are maximizing dt minus ds, which is ds minus dt. Like we are minimizing ds minus dt, which means that we are minimizing the shortest path, minimizing the path essentially. And here we are making sure that we are that the path between any 2 nodes is not greater than the direct arc. So inspired by this definition of DOIs, we can formulate the following observation. The shortest path from S to T passes through P, then so if shortest path from S to T passes through P, another node, then the subpath of from S to P and the subpath of from P to T are also the shortest subpath between these 2 nodes. How can we use this observation? So let me illustrate it on this example in particular. So if we have like a path from S to P that is a subpath of a bigger minimal path, then this path itself must be minimal. Therefore, the path that avoids it must contain a bigger total cost. So the next observation is telling us that if we denote dk of v to be the length of the shortest path from S to V, containing at most k arcs, then the dk of v, the path, the length of the shortest path from S to V, containing at most k arcs, is the minimum between 2 values. First, it's the length of the shortest path from S to V that contains a k minus 1 arcs, which means that adding the number of arcs does not affect the optimal length, or the minimal over all arcs over all nodes from which we can get to V of the value dk minus 1 of I plus civ. How to interpret this is with the following. So let's say that we have some node S, we have some node B, and we are interested. So we have some kind of network, and we have some path that within k arcs that contains only k arcs, and it brings us from S to V with the smallest kind of total cost. If we add, okay, so let be k minus 1. If we add one more arc, if we allow ourselves to go through one more arc, there are two possible cases. Either it didn't affect the initial optimal path at all, or it did affect, and in this case, since we still need to end up in V, we can consider all the ways through which we could have ended up at V, and consider all of that optimal paths from S to this nodes that contain exactly k minus 1 arc, and consider this last arc to be the kth arc. And our dk of V, since it must have passed through one of these arcs, it's going to be the minimum over this, like all of these numbers that are listed here. An expression of this form is called the dynamic programming principle. It's when the optimal solution of value for some problem can be calculated recursively from the optimum values of simpler or smaller instances of the same problem. Therefore, we can potentially, like if we need to solve a very large problem, we can probably solve a sequence of smaller problems in order to come together to end up with the large one. This recursive property that pieces the optimal solutions is called the principle of optimality. So this thing itself, this expression is called the principle of optimality. We're gonna be considering how to formulate the principle of optimality for many applied problems, including the uncapacitated load sizing and other important problems from operations research. But I'm not sure we have much time at this point. Yep, is there a question?
If the shortest path problem that we originally started with, if that's just a case of a minimum class network problem, that problem doesn't need to be solved by dynamic programming.
Exactly.
Okay.
Yeah. So the thing here is when the problem is easy, it's sometimes happens. It's actually often happens that it can be solved efficiently in many ways at the same time. So there will be multiple algorithms that are solving them like in polynomial time. In this particular case, it's the dynamic programming algorithm and also the linear relaxation algorithm. Both of them will succeed. At the same time, there are instances for which one algorithm would result in an optimal performance and the other would not. So it's not completely understood yet, and the area of science that does this is called the theoretical computer science. Very interesting stuff. I think we will stop at this point and continue next time. If you have any questions, I'll be around. Feel free to stop by.
You can short stuff, you need some like initial guess as to what the arc might be of like like some shortest path with like some large number of arcs, and then slowly find the best.
So it actually goes the other way around. Let me actually answer this question to the audience because it's a good question. So your question is how do we actually solve, like, use this principle of optimality? That's a very fair question. Normally, so first of all, a very important observation is that for an optimal path, it's unlikely to use more than n arcs on its way. Because if you are using more than n arcs on your way, it means that where n is the total number of vertices of nodes. So if you are using more than n arcs on your way, then you have come to some point, then you pass to another one, then you came back, and then you pass this one back, and then you back forward. You could just eliminate this cycle altogether. So first of all, you would never really go over d. So your solution is going to end at dn of v. This is going to be your end point. And then how do you use this? How do you get to dn of v? You first consider d1 of v. That's quite easy to do. First of all, so you consider this for all of the nodes in the graph. You find d1 of v for all v. We're gonna be, since we are only allowed to use one arc, it will be non-trivial. It will be less than infinity, only for cases where we like only for nodes that are simply connected to us. So if there are nodes that are simply connected to us, meaning that there's direct arc, for them this d1 of v is going to be less than infinity. For all other nodes in the graph that are not directly connected to us, this d1 of v is going to be infinity. After you have calculated d1 of v, to calculate d2 of v, you use this formula for all of the v's, for all of the nodes in the graph, and you continue calculating dk of v until you have reached dn of v, which is going to be equal to dn. Oh, sorry, d of v. Since you know that you cannot use more than n arcs.
When you run this on, do you get the shortest path at every edge?
Yep. You can extract shortest paths to every edges. It's quite easy to show that it's not, in fact, not possible to construct the shortest path from one edge to another if you didn't find the shortest path through all of the other edges, just because it's like the length of proof kind of argument. You wouldn't be able to prove that you have found an like the shortest path if you cannot just check like all of the other paths. But yeah, that's a good question. And then the eventual complexity of this algorithm. So on each step, you're essentially considering n nodes. So it's gonna be n squared because you do it n times, and on each step you consider n nodes. Good question. Any more questions? No? All right, thanks a lot.